Ladies and gentlemen, good morning. I'm President of the Hydrology section. I welcome you to the Spring 2000 Langbein lecture. As you may be aware, the Hydrology section has 2 awards to honor its members. One of them is the Hydrology Award, or used to be known as the Horton Section Award. And the other one is the Langbein Lecture Award, honoring Walter Langbein. And it is my pleasure to introduce the Langbein Lecturer for Spring 2000, our colleague Ignacio Rodriguez. I wonder how many people are in the audience that truly believe Ignacio needs an introduction. If there is anyone there, please have your hands up, so I'll give you about 3. Oh, okay. So I'll give you my email and I can send you the whole documentation on Ignacio. But anyhow, as I was thinking about it, I sort of felt a little nervous to come here and introduce you, and I said, why the hell am I nervous? He's supposed to give the talk. But you know, sometimes it could be intimidating, so I'm not going to look at him and I'm going to try to introduce him. He's had a very distinguished career, starting with his academic career at MIT as an associate professor, then moved back to the other, then down the road in Venezuela, in Simon Bolivar University, where he also acted as a dean. And then moved back to the U.S. to try to teach us a little bit more, and ended up at the Texas A&M University as a distinguished university professor and also an endowed chair, R.P. Gregory chair, and then also was the head of the civil engineering department there. Now, then he decided to come a little closer to the East Coast, and the last couple of years he's been at Princeton University as Professor of Civil and Environmental Engineering at Princeton and Director of Center for Energy and Environmental Studies. He has a long list of publications, hundreds and a number of books. And as far as his honors and recognitions, I don't want to read them all. There are a couple of pages of those practically. You can see every award AGU has had. And I guess we've been thinking about how we can keep his excitement in AGU. Maybe we have to create a few more awards for him. And believe me, that's the last one at least we have to give you, Ignacio. Okay? And this is not only what makes Ignacio so well known, besides being articulate and an incredibly talented colleague with many wonderful ideas that you'll see today. But I thought those were really things that made Ignacio famous until I ran into Eric Wood, who says, no, his greatest claim to fame should be that he was my advisor at MIT. Then, I was just discussing that a few minutes ago in the supporting members now, well, if you're not a supporting member, do become a supporting member, because that money goes to help the section. Till I ran into Juan Valdez, who says, well, no, he was my advisor too. So with that introduction, Ignacio is going to talk about hydrologic sciences tomorrow, complexity and self-organization in ecohydrology.
Thank you, Soros, for a very generous introduction. I'm trying to convince Soros to adopt me. But, I will be talking today about a topic dear to me, where I think that in years to come, there's going to be a lot of excitement in the field. And it's not the only topic, of course, but as I say, it's very much at the center of my present interest, and I think it will become very crucial. It's really the hydrologic dynamics behind ecological patterns and processes. And I will be centering my talk in water control ecosystems. I want to say this from the beginning. It's not that we are not all very fully aware that there are other things that also control ecosystems, nutrient process, competition for life, you name it. But in many ecosystems of the world, for example, dry savanna, shrub land, dry grassland, seasonally dry forest, and many of the most important ones, water is the controlling factor. And other factors like nutrient loss and accumulations and so on are so related and so coupled to the water dynamics that we have to start by understanding relatively well what goes on with the water. This is the group at Princeton, and I also want to name two persons that all live at Ecohydrology and Luca Ridolfi, Torino, University Politecnico di Torino, which are very much involved in this too. If I have to express the general objective of the talk with this one, is to improve the understanding of the spatial and temporal evolution of landscape scale ecosystems under varying climate and soil properties. So I will not be dealing with the particular details of plant physiology. Many of them I don't know, more than that. Many of them are not even known by the plant physiologists. I am not a plant physiologist to start with. But I think that for our purposes, in many instances, we can describe what goes on without getting into the microphysics of the problem. The challenges in this topic are indeed many. Challenges and tasks. When one sees a savanna or a grassland or, in fact, any kind of landscape, vegetation landscape, what immediately comes to mind that nature is hinting something at all. And the hint that is given is, there are grasslands in Kansas on the gradients of serious changes of rainfall are very much varying soil conditions. There are savannas which seem to be very stable, and nevertheless there is competition between grasslands and herbaceous and woody species in, say, in South Africa, and there are seasonally dry forests. Are they really stable? Why does nature prefer one over the others? These type of questions, as simple as they seem in appearance, are extremely complicated. And again, just by looking at the process, both the temporal patterns and the spatial patterns are going to observe in nature. This is a shrubland in Texas, and you see images of grasses, in this case with clumps type of trees, of woody species, but in many cases are not clumps. What does it tell you? What controls the spatial structure? What controls the temporal niches? What is the role of hydrology in this kind of phenomena is what I will be dealing with today. And as I say, the challenges are mutual, and the hints of nature are not as obvious as one would think. I mean, are not explicit. One has to look for them. What makes the search even more interesting. This is an example of that. This is from Bruce Mills, an ecologist in New Mexico, and from the American Naturalist Journal. And this is a remote sense grassland pattern from the Serengeti National Wildlife Refuge. And every one of those things is separated by 30 meters pixels, in which the coverage of their soil goes from 0 to 9%. The reason for this particular thing, I'm not going to get into that, is that in that range of coverage of grass and that range of their soil, a particular animal species is very abundant. So they were interested in looking at it. So this is the pattern of a special pattern of their, where in pixels 30 by 30, where their soil is between 0 and 10%, 0 and 9% in this case. And you look at that and you say, why the heck? Well, when one goes and again Mills did this and slides a window through this type of pattern and counts the number of those black pixels on square windows of different width areas, of course one will have a random variable. With a different windows will have different number of black pixels, of pixels that correspond to that type of quality, okay? This is what one finds. If this were a random map, this is what you will find. This will be the distribution. That will be the distribution. Here's one here. For a random map, and this is what is observed. Okay? Even more impacting like that. One says, well, it's not really random, huh? There is a lot of structure into that. That's a bit of nature. When one analyzes the moments of those first moments, second moments, third moments, things like these are found. Beautiful relationships in which the moments of the distribution with respect to the length scale of the window follow very strict relationships in power law of scale, indicating again a hidden structure that that is not apparent to the naked eye, but precisely because that is even more beautiful to find. And these challenges, these hidden messages, really do not bring order, an intrinsic order out of the apparent disorder that we saw a couple of slides ago. And I don't think anywhere better is described this task of this type of research than in the words of a very famous Argentinian writer, and somehow they will love this, which is Jorge Borges, in his famous Power of Babel, this wonderful library that contains every written word, every possible story that will have been written or will ever be written. And this kind of very messy thing, Borges finishes the library of Babel with this paragraph. If an eternal traveler should journey in any direction, he would find after untold centuries that the same volumes are repeated in the same disorder, which repeated becomes order. The order. My solitude is cheered by that elegant hope. And that kind of message, to find that order in that apparent disorder, which then becomes the order, is what is behind the search for the hydrologic dynamics responsible for ecological patterns and processes, I believe. The type of model that we'll be doing to pursue that hope expressed there by Borges in that quotation is schematically shown in here. I mean, one has a climate, soil moisture is the key variable in the whole thing, linking through soil, climate and vegetation, with some kind of multiple feedbacks and all kind of non-linear type of effects. Stresses on the vegetation which control the transpiration or lack of it, which in turn affect the soil moisture. Okay? So soil moisture has a central role in linking climate, soil, and vegetation. And the type of model I will be doing here, very much, at least in the spirit and many times also in frame, and in this type of framework, follow the path initiated years ago by Pete Dickerson and his group in MIT in hydroecological type of dynamics. Without getting into the equations, as I say, soil moisture is a controlling variable in this relationship, and it may act either directly on the physiology of the plant, acting, for example, in nitrogen directly, in nitrogen mineralization in the soil, or through the plant water potential, controlling the turgor, relative water content, and so on. The effect of all that is something which is called, in general, vegetation water stress, which may lead either to temporal or permanent damages. The modeling, again, to try to do quantitative, the challenges are of two kinds. One is the extreme complexity of the very large number of physical processes involved, and the other one, if I have to put my hand in two, is the enormously large variety of scales involved in the problem. We will tackle, or will attempt to do the tackling with a very simple model, which is simple and not so simple, in fact, which is an stochastic integral differential equation. It's a soil moisture balance equation. I always say that it's the most basic balance equation, most basic equation in hydrology, in which n porosity, zeta, depth of active soil. I will not go through these terms. We all know those terms. The stochastic driving mechanism is rainfall, okay, rainfall rate, which has intersection, of course, and the rainfall rate produces after intersection produces infiltration into the soil, which is both a random process and a very complex one because it's bounded. After the soil gets saturated, water cannot keep getting into the soil. This makes the mathematics of the process challenging, but this equation can be solved. Notice I am not considering here a strong lateral flow effect, which will be another challenge. If I have time, I will talk about that at the end, which will be the case on hill slopes in organized drainage basins. I'm not including lateral flow. I'm not including also interaction with the water table, because as I say, I will be dealing with water control ecosystems, generally semi-dry type of things. The water table in general is not that close to the surface. In fact, water table could be included. The mathematical is a little bit more complicated, but I am hopeful that that can be included. I am not so sure that the problem of the lateral flows can be treated in a closed analytical manner like this problem was treated. The rainfall is modeled at a daily time scale, and the colleague will say, my goodness, are you going to study effects on plants at the daily scale? I will say yes, because I am interested in the hydrologic impact on those. I'm not interested in the details of photosynthesis. I'm not interested in the details of how glucose is assimilated into the xylem. No. I am interested in how hydrologic dynamics drive those processes. So it's not a microscopic model, it's not a true large-scale microscopic modeling. This is a rainfall, there is interception, through fall, runoff, and infiltration into the soil. I will be considering interception of this kind, which is different for grasses or for trees, and of course varies from a species to a species. The type of losses that we will be considering in the balance equation are like this. We start at a hygroscopic point, there is no loss after the soil moisture is at the hygroscopic value. Then you increase just by evaporation from the soil to the wilting point of the plant. At the wilting point, you have an increase because the plant starts to transpire, and it transpires to a certain value, the maximum value at which that plant can transpire, potentially we want to call it an optimal atmospheric conditions, and in there it continues in a plateau until leakage takes over. And this is a leakage term, okay? From here down, from S star down, the plant is under stress. From S star up, soil moisture values above S star, the plant is not under stress, it's without water stress. S star is not fill capacity. It varies with the type of plant. And data is available, not a lot of data, but there is some data available. This type of thing has been corroborated several times. Very nice. This slide from a paper in, I hope it's pressed very soon, is by Guido Salvucci, University of Boston University, in which these are the losses for two different times of the year, and you see how similar is that loss function to the one we are assuming. This is, I mean, we are not discovering America here. The mathematics leads you to an analytically derived probability density function of soil moisture as function of vegetation, soil, and climate parameters. Those three things come into play in the probability density function, which is a closed solution to the problem, to the model that I just posed. And they look things like this. This is just a graph in which we have loamy sand and a sandy soil. Okay, this is the sandy and this is the loamy. And when climate increases and the soil varies in depth, you go like this. This is just an example of typical probability distributions. More interesting is again from Guido Salvucci, the following graph in which he compared without any fitting whatsoever, none whatsoever, the analytical solution with the observed points that he found for Illinois. Again, this is a paper being reviewed right now, and I thank Guido for giving me this slide and sending me a preprint. And you see how the analytical solution fits the point. One could say immediately there was some fitting or spotting there. There was none. We are doing modeling, and I think it's convenient at this moment to, at least spend 30 seconds in the philosophy of modeling. And I think it's good for hydrologists to reflect in what we search for when we do modeling. And I am particularly fond of this trait that I always got my students, which is the second one. I'm fond of both of them, and they because it's a good friend and a co-author of the paper of the probability density functions. But the one of Sankari, the purpose of models is not to fit the data, but to sharpen the questions. I would love it if hydrologists take to heart that phrase. But my own biased opinion is that I see a lot of models oriented towards fitting the data. And that's not where the excitement lies. The excitement lies in to promote models, in to search for models that will sharpen the questions, that will bring about the type of interrogations of questions now we don't even dream about today, that will help us to think in those questions and areas
that are not even disabled nowadays. I said, well, should they fit the data? Sure, they should fit the data. And even if they don't fit it very well, if they produce the type of questions that will drive science ahead, I will be very happy with it. But what I will really be disappointed with is when the effort of modeling goes towards fitting data. That's not where the gold medals are, that's not where the game lies. Again, I was talking about the hints of nature, and this type of modeling produces this type of result which has been corroborated. I don't have the data at hand. You see, when you, this is analytical, when you plot the variance of soil moisture for an homogeneous, say, 2 months type of thing, the early part of the growing season like Guido did, or the late part of the growing season, versus the parameters of rainfall, this is the rate of arrival of a storm event in events per day, and this is the average depth per storm event. You find for the variance of soil moisture things like this. In some cases it increases, but there are many cases in which it reaches a peak and then decreases. Telling you, which is kind of obvious after you think about it for a little bit, that there are climate combinations with some soil combination. It's the combination between plant, soil, and climate that will give you particular very high values of the variance of soil moisture. If you are a plant, if you are alone, you wouldn't like it. None of us want to have a lot of variance in the retirement fund or in the bank account. And this is the bank account of the plant, the soil moisture. If I am competing with another plant, I will like the other guy to have even a higher variance that I have. So this points towards this type of thing, and immediately bring us to another point. Say, fine, but that's for a season during a year. You are fixing the climatic parameters, but nature evolves in time. It changes throughout the years. And a good example, again, of a strong hint of nature is this one, the annual precipitation, how it changes throughout the year. This is an example from Alice, Texas. And this is the deviation in centimeters from the long-term average. And you see from 19 to 60, roughly 60, how a dry period, what a dry period existed in Texas, and what a wet period existed here, okay? I'm not going to try to model this. I'm just trying to point this out. And that is a spectacularly influential factor in this hydrologic dynamics and how it impacts ecological patterns and processes. To try to take it into account, we then go to this type of flow chart. Climatic fluctuations in rainfall, I'm not saying are of anthropogenic origin necessarily, just fluctuations. Variability in soil moisture, which we can tackle analytically under the assumptions made. And then we could go to a model of vegetation competition to see what's going on. In the case of Texas, this is again, you see the variation in the parameters of our lambda and alpha, rate of arrival of the storm events during the growing season. And this is mean depth of a storm event during the growing season. Look at that. There are growing seasons which have 0.17. There are growing seasons that have 0.4, 0.25. There is a lot of variation from year to year. And again, there is a lot of variation also in the mean depth of rainfall. This manifests itself analytically in the following. When you incorporate these variations analytically into the model, what you get is you can derive the probability distribution of the mean soil moisture. It's not now the probability distribution of the soil moisture. The probability distribution of the mean soil moisture for a growing season. And this is what you get. In the case in which you don't have a large coefficient of variation, in alpha and lambda, this type of distribution is this. But in cases like in Texas, these are very realistic. In fact, these are the coefficient of variation for low in Texas, for lambda and alpha. The probability distribution of the mean soil moisture becomes dramatically bimodal. Telling you again, watch out with describing things on the average something happens. On the average, it's a lot of baloney. Most of the time, you are not on the average, you are either dry or you are either wet. And that has been corroborated in practice. That is the type of sharpening the question that some modeling can do. And of course, the effect of this type of thing is, this is another example of how the probability distribution change. And of course, the change depends both on the type of vegetation and on the type of soil. And the effect that they have is like this. For example, in Texas, This is the percentage of woody cover in the 20 wet years, in the 20 dry years. The wet years, the dry years. The wet years, dry years. The impact of this type of thing in vegetation, in this type of ecosystem, you don't have to wait for geological time to take place. You can observe them very easily during the right time, and it changes the constitution of the ecosystem completely. Immediately, this brings us to the point that different type of vegetation responds with different type of dynamics to the soil, in basis of the soil moisture, to the type of demand that climate imposes. These are two typical traits. The sixth trait is for woody vegetation, for trees, shrubs, trees, okay? And the broken line type of thing is typically of grassland. I'm not going to get in here what type of grass, because they're very different also behavior from different types of herbaceous plants and different types of woody plants. But typically it's like that. Grassland or grasses tend to react very quickly to rainfall and decrease very quickly. They are very intensive type of users of the resource. Trees, woody plants, tend to react, but they run much more slowly, okay? Now, what is immediately evident that if you call the stress S star, the point below which you have stress, and S wilting, the point below which you have wilting in the plant, the crossing properties of the phenomena are going to be extremely relevant for what is taking place. So, for us it's crucially important to study this type of thing. The random variable described by the duration of an excursion above a threshold. This threshold typically for me here will be either the point at which there is a stress or the wilting point are two classical levels, or the amount of the volume in which of water density below the threshold, or very important, the number of crosses, down crosses, how many times you go under stress. You see, it's very different to go under stress very frequently, but not a heck of a lot of it. You come out of stress very rapidly, than to go into the type of stress that you will take you into depression for a long time, which is like a trip job, okay? But they are more resilient about the fact of going into there. So, what we did was to study, and I will not get into the details, analytically, these three random variables: number of crossings, length of excursions, and volume density, and describe moment-wise, analytically, this one, and one can derive the analytical properties of those random variables, and then incorporate them for the description of what I will call water stress. And water stress is a name that tries to include, and there is no better definition than that, all the damaging effects that lack of water has in the plant. Typically, one could say, look, water stress could be described like, I want this one only, okay, like this. Anyway, pay attention only to this. It's only after you are below a standard where you are in stress. And this is a normalization factor by S star and wilting point. And Q is not very sensitive to Q. You could have Q larger than, have to be larger than 0, but it's really be 1 or 2 to say, to try to reflect how the lack of water impacts the stress. Now you can also define, I will not get into the particular type of equation being used here, a dynamic water stress. Very different definitions, I mean, several different definitions will do the job for you, in which you incorporate, besides this static stress, you include the average time, the mean duration of an excursion below a certain point, a star at which the stress starts, the duration of the season, and the mean number of crossings of the particular level. When you incorporate all that, those are normalized values, okay? Normalized for the stress, both the static stress and the dynamic water stress, vary between 0 and 1. One of the reasons to do that is one of the goals, further goals later on of all this, will be to implement special models in which competition occurs in basis of the stress or lack of it that the plant experiences. Ecologists in general, which have done wonderful things in this type of models, will go probability of death of a plant, probability of reproduction of a plant, probability of colonization of a space, are taken ad hoc, are not related to the environment. This is where the role of the hydrologists come in extremely important. To define for them the linkage between those models, simplistic or not, with the external environment, with the climate, as function of the plant and the soil. One way to do it then, with this normalization between 0 and 1, is to say that the probabilities that we are going that will control a cellular automata in space will be directly related, in fact, can be themselves this stress or lack of it between 0 and 1. What we will do to start first, to start the implications of some of the implications of this modeling, is to look in detail at what is the impact of soil conditions and different plant conditions for climate like this. The example I have right here is for Texas again, on the crossing properties and water stress of the vegetation. That is easy to do. Mentally, the way we do the analysis like this, forget about the randomly, you take a sample of from the soil texture triangle, you take different type of soil, certain percentage of clay, sand, and silt, and then you calculate saturated hydraulic conductivity, porosity, B, which is the condition of the soil retention curve, this point, and T2A, the metric potential and saturation from the percentage of clay and sand, using, there are many relationships for those, some of them you will need more than others, but you can use whatever you want. We use here the ones of Vietnam. And then, from different plants or types of vegetation, you obtain the matrix potential and wilting, and the matrix potential at which stomatal closure begins. In this case, for the trees and grasses in Texas. Now, analytically, all those number of crossings, length of excursions, distances and so on, depend on those guys. So we need these guys in order to fit them into the equation, but we need them in such a way that they make sense. I mean that we are not assigning saturated hydraulic conductivity to things that, as you know, have no relation with the type of soil. So this is just outside the scheme, just to provide coherent type of properties of vegetation and soil. The type of results that one finds are like this. This is for the trees in the Texas dry period. And I don't have time to go from the number of crossings, I will concentrate in this, in the fitness. Fitness being just in 1 minus the stress. Again, it's just a word, and I don't like it very much, but let's call it 1 minus the stress, let's call it fitness. And you see that in the dry period, this is for dry, the dry period, 50 to 60, red means here high values. So red is high values of fitness, blue is low values of fitness. And there is quite a variation in the stress, which is again 1 minus the fitness. Okay? Between 0.27 to 0.6 or 0.575. Quite a variation in there. These are normalized values. Telling you, look, if you are in this part of the soil triangle, and if you are a tree during the dry period of Texas, you are really in bad shape. You are much better off the sandy conditions over here, okay, the red ones, okay? But there are many combinations that will give you this is the bad part, all this is good part for this, okay? Now, when you go to the wet period for the tree, you see, it inverts itself, and it makes sense again. If this is where you are in a better shape, okay? And this is where you are in worse shape. But look at something. The variation is very little. Telling you, when you are in a wet type of condition, with this type of things that we saw for Texas, and for in fact, this is for the trees which are prosopis, Prosopis velutina, Prosopis glandulosa, whatever, are the typical honey mesquites in Texas. For this type of tree, during the wet period, the soil does matter, but doesn't matter a hell of a lot. You're in pretty good shape, regardless of the type of soil. When you go to grasses, are very interesting to see. Grasses during the dry period are in better shape over here. Okay? They always are in better shape over here. You see, they don't like the sand. the little water they have will go very quickly to the bottom layers of the soil, and they are over here, okay? The variation is not very large, so grasses are very resilient to the soil in the case of Texas of this particular type of grass which is dominant in Lulis and in the research station of Texas A&M over there. And again, during the wet period, the best part is again in here. It doesn't invert itself like in the case of the trees. Fine. Now, one can do the following. Those qualitatively, those results make a lot of sense. Is to play a game in which we have 64 by 64 or whatever, and a square grid, and which we start with random soil, and we generate 100 years with the parameters of the wet period for Texas. And then, you see, we evolve year after year after year, and then we see, okay, let's see what kind of mean fitness, which again is the 1 minus the mean water stress that we have for the grasses here, and it varies between 0.58 and 0.53. Not a lot of variation, but some variation. In the trees, 0.5 to 0.6. So these two are very much overlapping. Telling you during the wet period, these trees are a little better, okay? But both of them will survive very happily. And the predominance of one or another will be commanded mostly by other exogenous factors like fire, grazing, etc., etc. When you go to the dry period in Texas, this is an example. And then here you see grasses go between fitness, again, 1 minus stress, 57, and it takes into account the whole thing, crossings, water deficit, length of extortion, between 47 and 57. Higher, some of them considerably higher than the ones of the trees. So during the dry period, grasses tend to do better. They are better adapted than the trees. And that is exactly what is observed in Texas, as I showed you in one of the previous slides. When you plot this in a different type of graph, you find this, you see, over 100 years simulations of dry thing, and this is analytical. Okay? This simulation is only a random sampling of the climatic parameters year after year after year, okay? Grasses dominate. If you are in the wet period, you tend to find some kind of equilibrium between trees and grass. But climate is not what you will call equilibrium fluctuation, meaning, hey, there is a lot of fluctuation from year to year, and the system responds more or less rapidly. So you will be oscillating between this thing, and this observed also in some of the data that Archer in Texas A&M and ecologists have. Now, questions that come in all this, let's try to sharpen the question. What climatic and adaptive factors favor the survival and reproduction of trees, grasses, shrubland? What favors the coexistence of both species? Coexistence is a very challenging type of phenomena, and has been traditionally explained by the so-called Walter hypothesis. Walter hypothesis is undoubtedly true. Trees tend to are more efficient in taking their water from deeper layers. Grasses are more efficient in taking their water from shallow layers. But it cannot be the explanation to the process. It's something that helps. Because even in cases in which you have an equal distribution of roots over the whole profile, typical example, nice level in South Africa, very well studied, there is coexistence between them, even more stable than in other places. So there are things going there which go beyond the Walter hypothesis. We can get data like this, what vegetation types are better suited to giving climatic and soil site conditions. You see, many in Northridge and many of the traditional ecologic pattern type of classification, you see in terms of, for example, temperature, which is a sort of a diagram by evapotranspiration probably, and rainfall. And they forest here, a grassland there, and they go all over the place. Quoting a good friend ecologist in Princeton say there are more the exceptions to those type of grass than the rules. So they have never gone, or just regression type of thing, they have never tried to incorporate the dynamics through really what counts in there. Soil moisture, in which the soil characteristics are an extremely important factor itself. Can the temporal fluctuations of climate percolation in the landscape. Percolation being clusters of vegetation that cross across the landscape and that allow different species to move from places to place. The phenomenon of percolation is well studied in physics, a space transition phenomenon, very characteristic of complex systems too. This is a complex system, a system made of many, many infinite quotation mark elements in space, vegetation and soil type, interacting locally under random conditions external in a very non-linear fashion. The hope again is that this type of interaction, the non-linearity of the system, and the local rules, which is what we are trying to find. One cannot play the game saying, let's impose some local rules. I find that just by passing the whole phenomena, and here is where I want to bring hydrology to the game. If what the hope is then that with the appropriate local rules, a natural self-organization will come out of that, like in many other complex systems. And then we could start studying quantitatively things like the possibility of percolation, or whatever other name you want to give it, fragmentation of a space, or lack of fragmentation of a space, the type of structural patterns in space and time, the niches in time, qualitatively defined through climate, soil, and vegetation. Type of data that is needed, I will put some examples here for three different types of ecosystem. One is all of them water, very much water control ecosystem. This is for Nightlet in South Africa, in which Brian Scholes and Walker have been, especially Scholes, have been very helpful in providing a lot of data. And these are this is a star. The transpiration is reduced below. This is volumetric water content. This is silent pressure potential. Wilting points are this. Look at how different are in the field, in this type of system, from the type of things you find in books, mostly done by soil-related agricultural people in the sense of studying crops. We are talking about wilting points in many cases on the order of 3 megapascals. Twice what is usually taken at 1.5. I'm not saying that 1.5 is completely out of order. No. I am saying that one has to go in detail and say, look, the Burkea africana is a woody plant, very controlling on the Nightlet in South Africa. It's close to -3, and it was very well measured by this guy. The Aragosti plant is almost -4. Those are high, very high wilting, very negative, very low, if you want to call it that way, wilting points. This type of data, we did a sample for several types of ecosystems. Concretely, the grasslands of Colorado, which is a very short grass semi-arid. The Nightlet, a typical savanna, with very stable coexistence in South Africa. And another example is the shrubland of Texas, the one I described before. The type of results that you get are these. And let me start with the Nightlet. What is the role of vegetation? Look at how different the probability distribution. Again, these are analytical results. This is not simulation. How different the analytical thing, at least through this model, and it doesn't seem to be that far off from the result of Guido Salvucci, and for Burkea africana, for the pulchra, 2 woody plants in the next level. The probability distribution is highly different, although the means are not that different. And that has important implications for the competition. Again, when you go to different types of grasses, this is Aragosti palus, and this is Italia rialta. Again, the mean one is not extremely different, it's different, but look at how different are the probability distribution. The impact of vegetation itself is very large. So vegetation controls soil moisture through soil, and soil moisture itself controls vegetation. This is a system with all kinds of nonlinear feedback. In the Nightlet, again, these are results analytically from, since we have, for whatever it's worth, the analytical expression for the crossing properties of the system. These are the dynamic water stress now, calculated for 4 vegetable species in Nightlet. Look, the crossing properties of the Burkea, Omna, Aragosti Italia are very different. But what is interesting is that the dynamic water stress is very close in all of them. That should be a hint of nature to tell us, look, that is one reason why it is so stable, the system. One doesn't seem to have an upper hand over the other. And not only that, the model results are very resilient to the only parameter, which is Q, which is a parameter which tries to reflect how nonlinear is the relation between stress and lack of water. This is with a linear one, Q equals 1, and this is with Q equals 2, and there is no big thing, no big difference. Now let's look at the case. The crossing properties for Holmes case, this is the prosopis, and Paspalatum in a Texas type of shrubland, or a Texas, they call it a Texas savanna for western triasia. T is the average duration in days, of an excursion below, in red, the point at which water stress starts, S-W. In blue is the point at which wilting starts, the wilting point. You see, in Holmes case, the average duration of an excursion in a stress condition is very, very high. And this is for the dry period, okay? Meaning, after you get, if you are in a dry, during the dry years of the record in Texas, if the Holmes heat gets into a stress, will last there for a long, long time. It doesn't react randomly. Look at during the dry period, the Paspalum savanna, the graph. The average duration is much shorter. Of course, if you are in a wet period, this one is cut in half, and this is diminished somewhat, okay? For the wilting thing, there's not a hell of a lot of difference, but this is dramatically different. Now, the number of crosses. Gases react much more quickly. In the dry period, you have per growing season an average of about 6 crosses of the level at which stress starts. In the wet period, you have even more, because we react very quickly. And here are corresponding values for dry and for wet. This is average number of crosses for the Holmes case, the prosopis. Again, much less. When you combine those two now into a stress, this is the dynamic water stress, theta, for Holmes case and Paspalum savanna, okay? And let's concentrate on the red one. This is the same thing. Again, they represent all the different values of the parameter Q. And you see the Holmes case during the wet period. Compare Holmes case and the graph. You see the difference is not much. During the wet period, they live together more or less in their happiness. During the dry period, the stress is considerably larger for the mesquite. The graph will have some advantage there. In terms of the water balance, this is what you get. Again, analytically derived. This is the Holmes case in dry period, wet period, Paspalum savanna dry and wet. And this is, look at the specifically most important is the evapotranspiration, non-stresses, which is this, and stresses, which is this. How different it is between different species, and how different it is between wet and dry periods of the day. When you get all this and you plot it, here is a plot of the variation of the water stress as function of the total incoming rainfall. Okay, total incoming rainfall for these two types of, this is the graph, Paspalum savanna, and this is the woody vegetation. You see, in the wet one, in the wet one, right, the Holmes case has a smaller stress, has advantage. On the wet, the dry one, the graph has a lower stress, has advantage. And in here, if you are around here, you live very happily together. So the closer that you are at this point, in the condition that you are in Texas, the closer there will be to a stable equilibrium. In that case, the case vegetation. In the example for the Shortgrass of the steppes of Colorado, the dominant species is about the water gracile, which is a very short grass, and it's well known. This is from Laura Ross in ecological application. The very last difference that exists in the reproduction of this plant. Look at this is the frequency of reproduction events is when you have wet years and when you have dry years. This graph, in fact, reproduces two ways, both via feed and also clonal type of reproduction. And analytically, you can derive, it's easy to show through the equation, that when you run through the equation, the fitness, which is again 1 minus the stress, versus the total growing season rainfall looks like this. As function of the soil looks like this. There are regions in which one soil is better than others. Another region when the other soil is better than that. And those things grow more or less, all of them are on the same region. Neumayer, in a very classical type of paper years ago in 1973, this is a quote from his, saying that the same vegetation can occur at lower rainfall. This was just an observation. Same vegetation can occur at lower rainfall on coarser soil than it does on fine one. The balance point between the advantage of coarser textures and the disadvantage occurs somewhere between 300 and 500 millimeters of rainfall. In this case, it is total growing season rainfall. It's about 70% of the annual rainfall in the steppes of Colorado. The balance points are, in this case, about 370 millimeters of rainfall here, which is again, is pointing that the model, the scheme of modeling, at least is pointing towards the type of question that one wishes to look at. Where do we want to go in this? And I'm closing now. Is we have probabilities now for normalized stresses and fitness. The game now is to have a special type of cellular automata, in which, as I said before, the reproduction, the life, death, colonization of the space around will be taking place year after year under varying climatic conditions, meaning different land and alpha, on the basis of those analytically derived type of probability. The hope, again, is that the type of structure preliminary results already show that there are conditions in which you have heavy clustering of vegetation. Other conditions, meaning woody plants, existing in a clustered manner in top of a matrix of grass. There are many other cases in which these clustering conditions do not occur. It's much more advantageous to have random type, isolate, even rejection type of pattern. There are cases, and this is not, it's not clear yet, in which we hope to detect the type of structure that I showed at the beginning of this talk in the Serengeti National Park. I believe that now we have at least started to get the handle in the local rules of interaction that will allow us to implement a complex system modeling to study possible self-organization in time and space of this type of process. So, thinking broadly what one does, and I have this done already, to generate two-dimensional fitness, or if you want to call it, stress fields for vegetation types in two-dimensional soil texture fields under interannual variations in growing season climate. Based on this fitness or stress landscape, determine the birth, death, and colonization. There are going to be a lot of obstacles and a lot of serious challenges in this road ahead. It's not as easy just even with cellular automata. It poses lots of complications. The objective, or the as much as one can, objective type of framing of this probability for the spatial interaction between the things. Nevertheless, I do hope, and I am fairly confident myself, that hydrology and hydrology are in a really special position nowadays, an extremely exciting moment to really take into account and assimilate all the hints that nature is providing us in terms of the temporal niches on evolution and the spatial structure of vegetation and its relation to the hydrologic dynamics. I hope we take those hints and we pursue this research line. And I would like to quote since I have been talking about the hints of nature, and I already quote an Argentinian writer, this I will finish with a great American. This is Robert Frost. Nature is always hinting at us. It hints over and over and over again, and suddenly we take the hint. I do hope that's the case, and I thank you all very, very much on the committee for allowing me to be here today. Thanks again.